Why does the determinant of a product equal a product of the determinants? So intuitively, we've seen that the determinant of AB really should be the determinant of A times the determinant of B. But let's make this precise. So here's the theorem. Suppose I've got matrix A, which will be an n by n matrix, and I've got a matrix B, which is also an n by n matrix. All right, then the conclusion is that the determinant of AB is equal to the determinant of A times the determinant of B. This is a theorem that we want to prove. There's a few different ways to prove this fact. Well, here's one proof. We're going to split into two different cases. One case is the case where the determinant of A vanishes, determinant of A is 0, and the other case is a situation where the determinant of A is non-zero. If the determinant of A vanishes, we're done. Well, why is that? Well, let's think about this case where the determinant of A is equal to 0. In that case, this matrix A is not invertible. Right? And because A is not invertible, A times B is not invertible either. Now, assuming that we have this understanding of how the determinant vanishing is related to invertibility, the fact that AB is not invertible, that then means that the determinant of A times B equals 0. And as a result, that means in this case we've actually proved exactly what we want to prove. Because in this case then, if the determinant of AB is equal to 0, then the determinant of AB being 0 is 0, which is the determinant of A, times whatever the determinant of B is. Now, each of these steps, requires some kind of proof. I mean, in particular, you have to already know how the fact that the determinant vanishes has something to do with it being invertible. But if you know these facts, then in this particular case at least, we've shown that if the determinant of A vanishes, then the determinant of AB is equal to the determinant of A times the determinant of... So there's definitely work hiding there. I mean, you have to know that if A is not invertible, then AB is not invertible. And you also have to be able to relate the determinant to whether or not the matrix is or is not invertible. Now, the other case is this case where the determinant of A is not 0. Well, what are we going to do in this case? So because the determinant of A is non-zero, that means that A is an invertible or non-singular matrix. Now what that means is that A row reduces to the identity matrix, right? Because A is invertible or non-singular, I can do row operations to reduce A to the identity matrix. Well, conversely, I could undo those row operations to transform the identity matrix through some row operations back into the matrix A. Now, the consequence of that is that I can actually express the matrix A as a product of elementary matrices. These are the matrices multiplication by which corresponds to doing a row operation. These are elementary matrices. And once I've expressed A as the product of elementary matrices that correspond to doing some row operations, well, then I could multiply both sides of this equation by the matrix B in order to deduce the following fact, that AB, the product whose determinant I'm interested in, is this product of elementary matrices times the matrix B. Now, why is that a helpful fact? Now, these become extremely useful facts in light of the following lemma. Namely, that for an elementary matrix E, the determinant of E times the matrix B is the determinant of E times the determinant of B. And this lemma is not too hard to prove. I mean, multiplication by an elementary matrix just corresponds to doing a row operation, and we already know how the determinant is affected by doing row operations. So this lemma is really just stating that the determinant of B with some row operation performed on it is the original determinant of B times the determinant of this elementary matrix. And it happens that the effect of doing a row operation exactly corresponds to multiplying by the determinant of the corresponding elementary matrix. Now we'll put this all together. Well, let's just think about the determinant of A, and we might actually reprove a fact you may already know. So the determinant of A is the same as the determinant of A times the identity matrix. This is just because A is A times the identity matrix. Multiplying by the identity matrix doesn't affect anything. But I'm working under the assumption that A is an invertible or a non-singular matrix, and consequently, I've expressed A as a product of elementary matrices E1 through EK. Now, using the lemma, I can express the determinant of this product in the following way. This is the determinant of E1 times the determinant of the rest of the terms, E2 through EK, times the identity matrix. And by repeatedly applying that lemma, applying it k times, I'll deduce that the determinant of A is the determinant of E1 times the determinant of E2 and so on till I get to the determinant of EK times the determinant of the identity matrix, which is just 1. Now consider the determinant of AB. We'll do the same thing. I'm looking at the determinant of AB, and assuming that A is non-singular, I've expressed A as a product of elementary matrices E1 through EK. But then using the lemma, the determinant of this elementary matrix E1 times the rest is the determinant of E1 times the determinant of E2 times EKB. And then repeating that lemma, I'll eventually conclude that this is the determinant of E1 times the determinant of E2, times the determinant of EK, and then what's left over is the determinant of B. Now we're going to put this together. Well, what do we get? Let's take a look at this. I've got the determinant of AB. I'll write that down here. Determinant of AB. Well, it's equal to the determinant of all these elementary matrices multiplied together. But that is the determinant of A. So this product of the determinants of these elementary matrices I can just replace with the determinant of A, and what's left over is the determinant of B. So, assuming that the determinant of A is non-zero, we've shown that the determinant of AB is the determinant of A times the determinant of B. And that means in either case, the determinant is multiplicative.